A galaxy spotted from the universe's infancy proves our timeline might be off, and the number one entry is something almost nobody guesses. Stay tuned as we count down the 10 earliest galaxies that are rewriting the story of the Big Bang. 10 billion years ago, a faint speck of light named MAX 0647 JD whispered that the universe formed sooner than we thought. Detected through the gravitational lensing effect of a massive galaxy cluster, this object appears at a redshift of about 10.7, meaning we see it as it was when the cosmos was merely 400 million years old. Its existence suggests that star-forming regions could coalesce rapidly, challenging models that predict a slower buildup of mass. The galaxy's luminosity, amplified by the foreground cluster, allowed astronomers to study its spectral signatures, hinting at early heavy element production. While still faint, MAX 0647 JD paved the way for deeper searches, and its discovery set the stage for even more distant finds that follow in this countdown.
Surprisingly, EGS Y8p7 shines from a time when the universe was just 600 million years old, yet it already hosts a mature galaxy with a well-defined disk. Recorded at a redshift of roughly 8.68, this galaxy was uncovered by the Hubble Space Telescope's deep field surveys and later confirmed with spectroscopic measurements. Its relatively high metallicity indicates that multiple generations of stars had already lived and died, enriching the interstellar medium far earlier than standard models predict. Moreover, the galaxy's mass, estimated at a few hundred billion solar masses, implies rapid accretion and efficient cooling mechanisms. Researchers continue to debate whether such massive structures could arise without invoking exotic physics or revisions to dark matter behavior. Up next, we look at a galaxy whose discovery relied on a cosmic magnifying glass, pushing the redshift frontier even further.
At a staggering redshift of about 11.1, GNZ11 stands as one of the most distant spectroscopically confirmed galaxies, dating back roughly 400 million years after the Big Bang. Discovered with the Hubble Space Telescope's Wide Field Camera 3, its brightness surprised astronomers because such an early galaxy should be too small and dim to detect. Spectral analysis reveals strong oxygen emission lines, indicating vigorous star formation and a surprisingly high metal content for its age. The galaxy's stellar mass, estimated near 10 solar masses, suggests that massive structures formed in a fraction of the time traditional simulations allow. Some researchers propose that GNZ11 could be part of a larger, unseen protocluster that boosted its luminosity. Its existence forces cosmologists to reconsider the efficiency of early gas cooling and the role of primordial black holes. Coming up, we explore a galaxy whose record-breaking redshift was only hinted at until the JWST arrived.
Hidden among the data from early James Webb observations, HD1, also catalogued as CEERS 1749, appears at an estimated redshift near 13, placing it a mere 330 million years after the Big Bang. If the redshift holds, HD1 would be the most distant galaxy known, challenging the timeline of galaxy assembly by several hundred million years. Its inferred ultraviolet luminosity suggests a star formation rate comparable to more mature galaxies, raising questions about how quickly gas could collapse into dense regions. Some analyses caution that the photometric redshift could be contaminated by dust-obscured lower redshift interlopers, so confirmation via spectroscopy remains crucial. Nevertheless, HD1 ignites debate about whether the first stars could have formed in massive halos earlier than predicted. Next, we turn to a galaxy that was uncovered using a different technique, spectroscopic blind searches that caught a surprisingly bright object at the edge of the observable universe.
Few people know that CEERS 1019, identified in the JWST source field, showcases a surprisingly mature stellar population at a redshift of about 8.7. Its spectrum reveals a pronounced Balmer break, a feature typically associated with older stars, implying that star formation began as early as 200 million years after the Big Bang. This finding suggests that not only did galaxies form quickly, but they also evolved complex structures much sooner than many models anticipate. The galaxy's mass, nearing 10 superscript 1 solar masses, further underscores the efficiency of early mass assembly. Researchers are exploring whether CEERS 1019 represents a rare, massive outlier or a glimpse of a broader population that JWST will soon uncover. Up next, we examine a galaxy whose discovery relied on the natural magnification of a massive galaxy cluster, allowing us to peer deeper than ever before.
Deep within the Hubble frontier fields, Abell 2744 Y1 emerged thanks to the gravitational lensing of the massive cluster Abell 2744. At a redshift of roughly 9.3, this compact galaxy shines with a luminosity amplified by a factor of about 10, making it visible to our instruments despite its extreme distance. Its spectrum shows strong Lyman alpha emission, indicating active star formation, and a relatively low dust content. The lensing effect not only boosted its brightness but also stretched its image, giving astronomers a rare glimpse at its internal structure, which appears clumpy and irregular. Such observations help refine models of how early galaxies built up mass under the influence of dark matter halos. After this lens-enhanced marvel, we move to a galaxy discovered via a blind spectroscopic scan that surprised scientists with its unexpected brightness.
Astronomers hunting for Lyman alpha emitters in wide-field surveys stumbled upon SILVERRUSH Z91, a galaxy at a redshift of about 9.0 that glows intensely in the narrowband filter designed for distant hydrogen emission. Its discovery was unexpected because the intergalactic medium at that epoch should be highly neutral, absorbing most Lyman alpha photons. Yet SILVERRUSH Z91's strong emission suggests that ionized bubbles around early galaxies were larger or formed earlier than many simulations predict. The galaxy's inferred star formation rate exceeds 30 solar masses per year, indicating a burst of activity that could have contributed to reionization. Its relatively bright magnitude also makes it a prime target for follow-up JWST spectroscopy. Coming up, we highlight a galaxy whose extreme redshift was initially hinted at by a single photometric dropout, leading to a dramatic confirmation.
Remarkably, GLASS Z131 surfaced in the GRISM lens-amplified survey from space, GLASS, as a faint dropout in the near-infrared bands, implying a photometric redshift near 13. Subsequent JWST observations have begun to confirm its extreme distance, placing it within 330 million years of the Big Bang. If confirmed, this galaxy would be among the earliest known, offering a direct window into the era of the first luminous objects. Its tentative spectral features suggest a modest stellar mass and a high specific star formation rate, hinting that even the tiniest galaxies could ignite quickly. However, the data remain noisy, and some analysts caution that low redshift dusty interlopers can mimic such colors. Regardless, GLASS Z131 pushes the frontier of what we can detect, and its study will test theories of early gas cooling and feedback. Next, we reveal the galaxy that currently holds the record for the most distant spectroscopically confirmed object.
Even after the JWST's first deep fields, HD2, also catalogued as CEERS 1749b, emerged as a contender for the most distant galaxy, with a photometric redshift hovering around 12.5. Its brightness, amplified modestly by a nearby foreground galaxy, allowed astronomers to extract a tentative spectrum that shows possible Lyman break features, supporting its extreme distance. If the redshift holds, HD2 existed when the universe was less than 350 million years old, implying that massive star-forming regions could arise almost immediately after the cosmic dark ages. The galaxy appears compact, with an estimated size of only a few hundred parsecs, and its inferred star formation rate suggests a rapid buildup of stellar mass. While spectroscopic confirmation remains pending, HD2 fuels excitement about the abundance of early galaxies that JWST may soon uncover. Finally, we arrive at the crown jewel of this list, the galaxy that truly rewrites our understanding of the early cosmos.
Finally, GNZ11, now reobserved with the unparalleled power of JWST, stands as the most compelling challenge to our Big Bang timeline. The new spectroscopic data tighten its redshift to about 11.1, confirming that we are seeing the galaxy as it was merely 400 million years after the universe's birth. JWST's infrared instruments reveal a surprisingly rich chemical composition, including strong oxygen and neon lines, indicating that multiple generations of massive stars had already lived and exploded. Moreover, the galaxy's stellar mass, nearing 1 billion solar masses, and its high star formation rate suggest that it assembled its bulk in an exceptionally short period. Such maturity at this epoch forces theorists to revisit models of gas cooling, dark matter halo growth, and the efficiency of early star formation. GNZ11 serves as a benchmark for the next generation of cosmological simulations, reminding us that the universe's infancy may have been far more dynamic than we ever imagined.
We've journeyed from the faint whisper of MAX 0647 JD to the astonishing brightness of GNZ11, each galaxy nudging the limits of how quickly the cosmos could assemble. These discoveries remind us that the universe still holds secrets that can upend even our most cherished theories. If you enjoyed this countdown, hit the like button and subscribe so you won't miss the next mind-blowing list we release each week. Which galaxy left you the biggest impression? Was it the record-breaking HD1 or the mysterious GNZ11? Share your thoughts below. I love reading your perspectives. Thanks for watching, and see you in the next video.